Okay, so this video is going to be the proof of the law of sines. Why do we need the law of sines? So we can use our basic trigonometric ratios of sine, cosine, and tangent to solve triangles, which means if you're given certain side and angle information, you can use those ratios to find all the rest of the sides and the angles. However, those only work for right triangles. And it would be nice if we had a way to solve all triangles. Whether the triangle is right, acute, or obtuse, I would like to be able to find its missing sides and missing angles. So in order to write a proof that would work for every type of triangle, I need to break this proof down into three categories: acute, right, and obtuse triangles. So I'm about to work through the proof for each case. Okay, I'm going to start with an acute triangle, and I've labeled it ABC. Remember, an acute triangle has all three angles less than 90 degrees. So the vertices are labeled with capital letters, and then across from the vertices are the sides, which are labeled with lowercase letters. So across from vertex A is side A, and so on and so forth. And you'll notice that I've already drawn an altitude from vertex A to side A, and that's going to represent the height of my triangle, and I've labeled it with an H. So now what I'm going to do is come up with some relationships which are true for this triangle and use those relationships to come up with the law of sines equation. So first of all, I'm going to concentrate on the right triangle that was created with this part of our acute triangle. And because that's a right triangle, I can use the sine ratio, where sine is opposite over hypotenuse, and the opposite would be h, and the hypotenuse would be c. So the sine of angle B is h over c. What I'm going to do next is use the right triangle on the other side of our acute triangle. So I'm going to use this one. And because it's a right triangle, I can also use sine, cosine, and tangent relationships. And if I'm interested in the sine of angle C, then its opposite over hypotenuse will be h over b. So notice that I've created two equations that both involve h, and then they involve other sides and angles of the triangle. So what I'm going to do with both of these equations is isolate h. So in the first equation, if I multiply both sides by c, I will isolate h. And in the second equation, if I multiply both sides by b, I will isolate h. Now, if h equals one thing and h equals another, then the first thing equals the second. So we can say that c sine of b is equal to b sine of c. And then just to change the form of that equation somewhat, what I'm going to do is divide both sides of the equation by the sine of b. And I'm also going to divide both sides of the equation by the sine of c. So if I do that, what you'll notice is that you can cancel the sine of b from both sides, or from the top and the bottom of the left side, and you can cancel the sine of c from the top and bottom of the right side. So what do we have left? We have c over sine c. So side c over the sine of angle c equals side b over the sine of angle b. And that gives you a relationship between those two parts of your triangle. Two angles and two sides. But what about A? So what I'm going to do next is take the same exact acute triangle and do a very similar kind of thing, but I want to incorporate A into the work in some way. Okay, so this is the exact same triangle, but I've drawn in a different altitude. So this time I'm going from angle C across to side C and dropping that perpendicular. and I've labeled the length of it k. So I'm going to do something very similar. Notice that the altitude breaks our triangle into two right triangles. So if I take the right triangle that's here, because it's a right triangle, I can use sine, cosine, and tangent relationships. And the sine of angle A would be its opposite over hypotenuse, which would be k over b. And I'm going to do something very similar using the other triangle, the other right triangle, the top one. And since that's a right triangle, I can find the sine of angle B by taking its opposite over hypotenuse, which would be k over a. Now, hopefully this is starting to look familiar. It's looking like what we did in the first part of the proof. And I have two equations that both involve k. They also involve other angles and sides of the triangle. And what I'm going to do is multiply both sides of the first equation by b to get k by itself, and multiply both sides of the second equation by a to get k by itself. And since k equals one thing and k equals another, we can set those two things equal to each other. And then we can divide both sides of the equation by sine of a, and divide both sides of the equation by sine of b, just like I did in the previous part. That just makes things rearranged a little bit and gives us a more user-friendly form. Cancel the sine of a's on one side, cancel the sine of b's on the other side, and we have side b over the sine of angle b equals side a over the sine of angle a. And if you put all three of those ratios together, they're all equal to one another. So you can use any two of those ratios that is helpful to solve the problem that you have. Okay, well that's a great proof, but that only proves it for the acute triangle. So I still have two cases to look at. I need to look at the right triangle and the obtuse triangle and see if I can come up with the same kind of relationship. I'm really hoping that the same relationship holds no matter what kind of triangle I have, because I would like to have a rule or law that works for every kind of triangle. So next I'm going to look at the right triangle, and I've chosen to let angle C be the right angle. And because this is a right triangle, we can use regular sine, cosine, and tangent trig relationships. And the sine of angle B would be its opposite over hypotenuse, which would be B over C. The sine of angle A would be its opposite over hypotenuse, which would be A over C. And the sine of angle C, well, that's a tricky one because angle C does not have an opposite. Angle C is the 90-degree angle, but we can just write that the sine of C is the sine of 90, and we know from our previous work that the sine of 90 is 1. Okay, now my hope is to come up with the same relationship that we found for the acute triangles. So what I'm going to do is take these first two equations and multiply both sides by c. So I have c sine of b equals b, and c sine of a equals a. And then I'm going to isolate c. c equals side b over the sine of angle b, and c equals side a over the sine of angle a. Okay, well this is good. If c equals one thing and c equals the other, then one thing equals the other. So we have little b over the sine of angle b equals little a over the sine of angle a. That's good. That's the same relationship we found for the acute triangle, but we still want to incorporate angle C in there as well. So we know that both of those are equal to C, and I would argue that C is equivalent to C over 1. And we just noted that the sine of 90 is also equivalent to 1. And angle C was 90 degrees, so the sine of 90 is equivalent to the sine of angle C. So there we have all three ratios equal to one another for the right triangle. So we're making good progress. Now we just need to prove it for the obtuse triangle, and we will have this relationship is true for any kind of triangle. So I've drawn an obtuse triangle. Just focus on the one at the top for now. And I've dropped the perpendicular from angle C to side C. And so that gives us a height, and I've labeled it with an H. And I'm just going to concentrate, first of all, on the right triangle formed here at the top. And because it's a right triangle, we can use sine, cosine, and tangent relationships. And the sine of angle B would be its opposite over hypotenuse, which would be H over A. And then if I move down and use the other right triangle that's created, we have another opportunity to use the sine, cosine, tangent relationships. And if I want the sine of angle A, then I take its opposite over hypotenuse, which would be H over B. Okay, now this is going to look very familiar. We did this in the first case. We isolate H in both cases, multiply both sides by A to isolate H, multiply both sides by B to isolate H, and H equals this and that, so we set this and that equal to each other, and we get A sine of B equals B sine of A. And you can see what's going to happen. We saw it earlier. Divide both sides by sine of B, divide both sides by sine of A, and you get A over sine A equals B over sine B. So we are almost there. We just have one more part to include, and that would be how to incorporate the C's into this case. So this is why I have a second version of my obtuse triangle drawn with a different altitude drawn in. But remember, when you're drawing an altitude to one of the acute angles of an obtuse triangle, it actually goes outside the triangle. So the altitude that I'm talking about here is this, and it goes outside the triangle. If you want to go from angle A to the side A, well, you have to extend side A and then go outside. So what I've actually done by making that extension, we call the dotted line here an auxiliary line, is I've created a right triangle. And so we can use sine and cosine and tangent to figure out the, lost my train of thought there, to figure out some relationship between the parts. Okay. Now, I'm going to go back actually, and I'm going to do the other triangle first. It will be easier. We'll save that one. So looking at the right triangle, the big right triangle that was just created using the auxiliary line. Because it's a right triangle, we can use sine, cosine, and tangent relationships. And the sine of angle B will be its opposite, which is K, over its hypotenuse, which is C. And now moving on to the trickier one, this would be the smaller right triangle that I was looking at earlier. Okay, so what I want to do is find the sine of this angle right here. The sine of this angle right here. Well, the angle over here was angle C. Together we have a straight line, so this angle right here is 180 degrees minus C. So the sine of 180 minus C would be its opposite over hypotenuse, which would be K over B. So now we have two equations that both have K in them, and we can isolate K and move on from there. But I want to remind you of something that you heard in class, where we were exploring the sine of, say, 40 and the sine of 140, and we found that they were equal. And you could pick any number like the sine of 2 degrees and the sine of 178 degrees, its supplement, and you would find that those are equal. And so you can generalize that the sine of an angle is equal to the sine of 180 degrees minus the angle. So that helps us here because the sine of 180 minus C is equivalent to the sine of C. Okay, so now we're going to isolate K in both of these equations. K equals C sine of B, and K equals B sine of C. And you can see it's almost done because if we set these equal to each other, and then divide both sides by sine of B and divide both sides by sine of A, we're going to get C over the sine of angle C equals B over the sine of angle B. And above we had that b over the sine of b is also equal to a over the sine of a, so all three are equal to one another. So that is the law of sines for any triangle, acute, right, obtuse, any triangle with side lengths a, b, and c and corresponding angles a, b, and c. This ratio relationship holds. And when you go to use it, you're just going to use whichever two of the three ratios are helpful in that problem. Now this won't actually solve every triangle. It will only solve the triangles where you have the correct combination of given information. Like if you know two sides in one angle, two sides in one of the angles you need for that ratio, then you'll be able to solve. But if you have, say, three sides in one angle, or just three sides, or three angles, you won't be able to solve with the law of sines. However, there's another law coming that will give us more opportunities to solve triangles. So there you go, we have our proof of the law of sines. Thanks for sticking with me.